Hi, my name is Jonathan Blanchette, and this is a presentation on convolutional rank filters in deep learning. This presentation is part of my PhD work. I've designed novel layers, so adaptive rank filters, simply named rank filters, and adaptive transposed rank filters that I'll name transposed rank filters for short. They are adaptive because the weights learn to optimally combine ranks in a neural net with stochastic gradient descent, for example. I had to design the layers with CUDA because the building blocks just aren't available in machine learning libraries. This is the layout of the presentation. I'll explain the goal of the study, and I'll go through vocabulary and the rest of the motivation for the work. I'll present the clockwork of rank filters, and I'll quickly go through transposed rank filters. Then I'll talk about the performance and the findings, and I'll conclude and open the topic on other nonlinear filters. Rank filters are not new. They are already in widespread use in the state-of-the-art neural networks, under the disguise of max pooling. They have advantages such as downsampling and local robustness. So what I mean by robustness here is the invariance to change in input intensities. They also make intuitive sense. So to pass the highest activation makes intuitive sense. But they also have pitfalls and weaknesses, as explained in the CapsuleNet article by Jeffrey Hinton and his team, and also by the article that proposes of using only convolutional blocks with no max pooling whatsoever. The study aims to systematically explore advantages and disadvantages of using rank filters. They're used haphazardly based on intuition as to why they might be useful. CapsuleNet is no exception to this rule. It uses routing by agreement, which discards capsule outputs that doesn't agree with the maximum mode. Okay, the intuition here is very similar to the one that motivated the use of max pooling, where we pass the maximum value of a small region. So both discard information. Remember the article that proposed simplicity by not using max pooling? Well, there is one that proposes the same for capsule networks. It's called Pure Capsule Networks by Chen and others, introduced in the article entitled Capsule Networks Without Routing Procedures. Their team actually showed that the main achievements of great results of capsule networks is the leap to an extra dimension achieved by a generalized convolution. This is explorative work. The main purpose of this study is to learn the properties and behaviors of this family of layers in order to understand it better. It will provide valuable insight enabling future architectures with more informed use of rank filters as a critical component within an architecture. This is a small analogy table between the routing by agreement and max pooling layers. It shows the intuition that we puny humans really like because it's easy to understand compared to the black box model with a network that only uses convolutional type layers. For max pooling, we pass the highest activation. It's used for downsampling, but I really hesitated of including this as an advantage. It really is just a feature, because there are other ways of downsampling, say for example if you use a strided convolution instead. It is robust, but as a consequence of this highly robust feature is that it comes with discarding too much information. For capsule nets, we route the highest probability vector feature, also named capsule. It yields great geometrical features, but as previously mentioned, this can also be explained by the higher order convolution. It is robust, but as a consequence, we need to discard information as well. So we can make a similar table for rank nets. They don't only use the highest activation. This is a biased assumption. We will let our black box model decide if it can make good use of the activations that are second highest and third highest, etc. It may learn to be robust if the weights are small. So we let the net decide what information to discard. Hence, this is an unbiased model in the sense that it is less restrictive. Now remember that this is explorative work, so later on we will recap on this table in the results section and add more advantages and disadvantages. So let's start with a little vocab first. So what is a deconvolutional net? So right here you have one designed for segmentation. On the left you have the coder that downsamples and encodes the signal into a latent code, or simply code. So the code is the bottleneck in the middle. The encoder has convolution layers and max pooling layers. On the right, you have the decoder that reverses the operation of the coder. In other words, it transforms the code into an output. So in this case, the output is a segmented image. The decoder usually consists of transposed convolution, and it can have max unpooling layers. I'll talk about these later on. Also, deconvolutions are synonymous to transposed convolutions, so it's the same thing. You can call them transconvolutions if you want. And what are ranks? Well, you take a sequence, you order it, the sorted values are your ranks. That's it. And to get the ranks, you need to do a nonlinear operation, because you can't linearly combine the initial sequence to order it. It doesn't make sense. And it's a data-dependent transform. So because the permutations to sort the values depend on the values themselves. So that's a no-brainer. And what are rank features? Well, rank features are outputs of rank filters. Some of the filters include median filters, max filters, min filters, or it could be a linear combination of those, or anything else, any combination of the ranks. So here is an example picture that I took back in Italy of a crazy horse. So that's the output of a median filter. Here you have the output of a max filter. So here is the output of a min filter. So that has the effect of dilating minimum values. So now the horse is on ecstasy. Or you could have range filters. Those were used back in the days as edge detectors. And why not? You could combine like information of the ranks between the channels and combine them together linearly to get something weird. So rank filters generate new features for neural nets. So the nonlinear features include dilations and contractions. Rank filters generalize many layers. But what do I mean by generalize? Suppose you have a group of objects, say a bat, a mare, a whale, a chimp, and a platypus. Well, you first look for the similarities. They all have nipples. Wait, okay, maybe not the platypus, but they all have mammary glands. So you can generalize the group as mammals, with maybe a little reject section to exclude the nippleless, egg-laying, venomous critters, such as the platypus. Sorry, platypus. So now consider another example of generalization. So if you look at a square, a triangle, and a pentagon, well, you look at the similarities. What group could generalize them? Well, polygons. So we will go through the same process and look at layers to check the similarities and figure out the broader family picture. The rank filter family includes max pooling, median filters, and also rank pooling that was introduced back in 2016. Average pooling is also a special case of rank filters, but it can also be reached by linear convolution. So the circles you see right here are supersets. So the adaptive rank filter family, it can learn to become max pooling. It could learn to become any of these instances within the rank filter family if that's the optimal choice. And the weights acting upon the ranks can be anything. So they can be positive, they can be negative too. The max pooling layer was designed to downsample and pass highest activations from a small patch. Hence, the field of view is always equal to the stride. It's a robust layer because small changes in the input patch may not be transferred to subsequent layers. On the left, I've highlighted an input patch. In the middle, you have patches sorted from smallest to largest values. Then I perform a dot product with weights that only keep the max. Highlighted in red are the ranks, so these are sorted values in column order. So the first block, there was no change because it was already in order. For pooling layers, the field of view is always equal to the stride. So there is never any overlap between the windows. The weights in max pooling layers are static, but since this is a rank filter, an adaptive rank filter layer, it can learn the 0001 weight. So it can learn to pick only the maximum. In average pooling, the weights average local pixel intensities together. By the end of the training, if the rank filter learns to average all the pixels together, then it has implemented average pooling. But average pooling can also be learned by linear convolutions. So this is why I've placed them within the intersection of the linear convolution superset and the rank filter superset. Back in 2016, the authors of rank-based pooling designed a downsampling layer that learns to pick ranks. I've just shown various layers under a rank filtering perspective. Matthew Zeeler and Rob Fergus have introduced max unpooling layers in 2014. They use these in deconvolutional neural nets. Now, deconvolutional layers really are transposed convolutional layers. And by analogy, max unpooling layers are transposed max pooling layers. We will make the same analogy, and hence transposed rank filters generalize max unpooling layers in the same way that rank filters generalize max pooling. Yeah, maybe that sounded a bit confusing. Anyways, robust filters may be advantageous, so we will explore this if indeed it is advantageous. The nonlinear filters I'm presenting learn to combine ranks as opposed to fixed max pooling and average pooling. So the rank filters learn nonlinear features such as dilation and contraction. The rank filter family is not constrained to only downsample, and the output number of channels is not necessarily equal to the input channels. This means that the filter is very similar to a convolutional layer, in the sense that you are free to choose the stride, the field of view, and the number of feature maps. I'll start with an example that uses a 3x3 field of view with a stride of 1. So just as before, in the middle, you have the patches containing the ranks. Then we perform a dot product with the weights that can be learned. The stride is 1 over the input, but each patch has a field of view of 3x3, so the stride over the rank should be 3 across the height and width dimensions. The weights can converge to any value, positive or negative. This is an example input. So these are the rank patches inside the boxes to show you where the dot product takes place. So in this case, the patch size is 5 by 5. So in this second example, you may still downsample by skipping some patches. So in this case, we pick 1 and 2 patches. And why not? You could also have a rectangular field of view. So in this case, the patch size is 1 by 8. And inside each box, you will see the ranks sorted from smallest to largest values, from left to right. Okay, I'll briefly introduce transposed ranks. So if you want any more details, you can check the extra slides at the end of the presentation. But just as with transposed convolutions, you can get artifacts. So as for max unpooling layers, transposed rank filters use memory of the encoder. For strides coprime to the field of view, artifacts may occur as you just saw. So there was a solution that was proposed by Yusuke Sugawara and his team back in 2018, but I used a different approach. While working with transposed rank filters, we've discovered that they were best placed immediately after the encoder counterparts. So we don't stack encoders and we don't make stacks of decoders. So this is a big no-no. So what you want is actually a rank filter immediately followed by the decoder. And you could use these as a block, as a building block. Now, since you can use the coder-decoder pair as a block, you can stack the blocks. And although nonlinear, both layers perform better with an activation immediately after. So whatever applies to linear convolutions or transposed convolution also applies to rank filters and transposed rank filters. We also noticed that the best results were obtained when the field of view was either 2 or 3 and when the strides were small. We've conducted an experiment to see if neural nets with rank filters were more robust than the linear convolutional net. So in this experiment, we trained both autoencoders with a total depth of 11 layers with skip connections and all. So we trained both nets with a database that had 50% chance of having one of their channel pixel values corrupted. And it was corrupted by a Gaussian mixture noise with 3 modes. So really the database, an image from the database really had a 12.5% chance of having its pixels uncorrupted. When the denoising autoencoders were finally trained, we tested on a data set of images with varying degrees of corruption rates. So that is that's what's shown in the graphic. To our surprise, the linear net performed better than the rank net, but when we varied the corruption rate, the L1 loss of the linear net started to grow after some point, while the L1 loss of the rank net steadily dropped. So we can ask ourselves the question, if we ignore all the permutation at the decoder, so instead of using a transposed rank filter, instead we use a regular deconvolution, will we get a better performance? So the answer to this question is it depends. It depends on so many things. It depends on the field of view, the stride size, and the network depth. And as I already mentioned, if you really want to use stack decoders, well, you're just better off to use plain deconvolution. So the sorting algorithm can be quickly executed in a GPU if the field of view isn't too large. But as I already mentioned, it's better to use the field of view that are 2 or 3, so that's not too large, and so the algorithm performs quite quickly. So I've conducted another experiment where I've trained 2 shallow denoising autoencoders. So there are just 2 levels. The rank-based autoencoder performed way better than the all-linear layer. So you can see this at the bottom images. Right here, we've conducted another experiment to see what happens when we increase the total depth. So we use the depth of 4 because we've designed our nets to have 2 stacked pairs of encoder-decoders. Again, the rank autoencoder performed better than the all-linear net, but you can see that the all-linear net catches up. Another thing we found is that transposed rank filters can't encode as much information as plain convolutional networks, but that is expected since ranks are highly correlated, and so should be the weights. So to show this, we've trained 2 nets to classify MNIST images, and both nets had a total depth of 10. 1/4 of the capacity for the rank net were reserved for rank features, but the all-linear convolution net performed better than the rank net. So this shows that rank features do not convey as much information as the linear nets. So you can see here that rank filters are highly correlated. So this is an example. On the left, you have rank filter weights. So you can see a pattern. So the 3x3 weights were arranged in a column, and that does make sense because there is no geometrical information in rank filters. It's only about the size. So on the top you have the weight with regards to the smallest value, and on the bottom you have the weights associated to the max value, and in the middle for the median. And on your right you have the transposed filter weights, and you can see again the same pattern emerges. It's highly correlated. So rank layers learn robust features. They generalize many layers already used. Ranks are inherently correlated, as you just saw, but we've noticed that rank weights weren't as much correlated compared to the weights of neural networks that didn't perform as well. So if they're highly correlated, it's a bad sign. Also, rank filters perform best for networks of depth smaller than 5. And this had, you can see shallow networks occur in neural net cascades. Also, rank filters are an example of data-dependent nonlinear filters. So there are many data-dependent nonlinear filters in the literature. Histogram-based methods is one of these examples. So the Hog features histogram equalization is one of those. And it is possible to use them in deep neural networks. So it is possible to derive backpropagation algorithms for these. ReLU layers and concatenated ReLU layers can also be modeled with histogram filters. ReLU is the simplest one, so it requires only a single infinite bin from 0 to infinity, and concatenated ReLU layers uses 2 bins. So it includes also the negative values. So that's the extra bin. Another research topic would be to investigate higher order convolutions. So the authors of the pure capsule nets use a higher order convolution. Perhaps we could get even better results if we leaped even further to higher order dimensions. This is the same table from slide 9 where I've completed the advantage and disadvantage sections. So important lessons to keep in mind from this presentation is to keep stuff simple with maybe a few exceptions depending on the task you have in hand. And you keep it simple by using linear layers. There is no need of adding a nonlinearity such as routing or max pooling or max out. The linear layer does the job, and ReLU is already a very useful nonlinearity. So can we make a prediction with the rank filter behavior? Well, we can expect that for deep layers with or no skip connections, pure capsule nets will surpass capsule nets in the same way that linear layers are superior to rank layers. Designing a neural net is like composing music. Suppose you're a classical music composer, you write a song with multiple partitions, and you rehearse with a band, but you feel something is missing. So what do? Would you base your correction or add a new partition based on the loudest musician or the loudest note at a given time? No, of course not. You need to listen to the song as a whole to get the gut feeling of what you need to change. Neurons are like musicians, and we need to start to view them as such. So artificial intelligence is like a neuron symphony. Here I bring up the maxon pooling layer used as a transposed rank filter. In maxon pooling layer, we need to save positions from where the max came from. Then you need to upsample the code highlighted in orange, so that's the input to the maxon pooling layer in the middle. So you upsample with the same weights that encoded a max operation. So that's the weights are 0, 0, 0, 1. Then at the last step, we permute the values back from where they came from. The permutations come from the coder. Note that this is just for illustration needs, so this is really overkill to show how max pooling can be modeled by a transposed rank filter. So you don't need to know all the permutations. You just need to know the max position. So that's what Matthew Zeeler and his team call switches. So I'll illustrate the inner workings of a transposed rank filter with a field of view of 2 by 2 with a stride of 1. So the input to the decoder in the middle is upsampled on the right, highlighted in red. So you see the input upsampled by the weights arranged in a 2 by 2 matrix with the values 0.2, 0.5, 0.5, and 1. Then on the top left, highlighted in green, the next operation is to permute the values back from where they came from. Then at the bottom, we overlap and add. But actually what we're going to do is we're going to overlap and average. So if we add 2 terms, you divide by 2. So if you add 4 terms, you divide by 4. And when I say multiply by the maximum overlap, so in this case, the maximum overlap is 4, because in the middle of the matrix, there were actually 4 values that contributed to that value. So that's 10, 7, and 2 zeros. So the total number of terms was 4. So that's the maximum overlap in this case is 4. So you multiply the overlapped and average by 4, and you get the output of the decoder.